All right, we are back here, Unit 3, Topic 4, Ideal Gas Law, changing things up a little bit. For the first, three topics there, we had been talking about intermolecular forces, particularly talking about solids and liquids, really a lot about solids, right? And how those intermolecular forces keep those substances in solid form, right? The interactions that come into play there, whether it be ionic or dipole-dipole, things like that. What we're going to be talking about today is the third state of matter, okay? And it's really not going to have a lot to do with intermolecular forces. So a little bit different. We're going to be spending a couple days talking about gases. And so today is a little bit introductory, but there is just a lot to go over. So bear with me. This might be a little bit of a longer video, but I'll try to make it not too bad. The objective here is to explain the relationship between the macroscopic properties of a sample of gas, meaning pressure, volume, temperature, moles, and gas constant, which isn't really a property, but using the ideal gas law, okay? So we're going to be talking about this equation here, PV equals nRT. You may have seen this before. We're going to be talking about partial pressures, which are pretty simple, and we're going to be talking a little bit about some graphical representations between these different terms, pressure, volume, temperature, and moles. But yeah, like I said, it's sort of an introductory day when it comes to gases. We'll be diving a little bit deeper into this next time as we talk about kinetic molecular theory. All right, so we are going to have a problem-solving video, FYI, because I do want to show you some examples of how to use the ideal gas law. In terms of our slides here, we're going to be talking about pressure, what that means. Okay, pressure is sort of one of these terms here. It's one of these four things that you probably know the least about. Volume and temperature are sort of intuitive. A lot of you sort of know what moles are already, right? Just the amount of substance. Pressure is not as intuitive, so we're going to be spending a little bit of time talking about that. We'll go over its units, different ways to the different units that are used in measuring pressure. We'll talk about partial pressures. Then we'll get into some gas laws, what it means to be ideal, okay, what an ideal gas is, and then finally we'll wrap things up with a short discussion on the ideal gas law. And then, like I said, in the problem-solving video, we'll actually use the ideal gas law to solve some problems, right? Okay, so pressure. All right. Gases uniformly fill containers. Okay, so gases, if they are left to their own device, they will fill up a container, whatever container they happen to be in. All right, they're easily compressed or expanded. Okay, the particles of a gas are usually few and far between. There's lots of space in between the different particles, so they're easily compressed or expanded. And gases also will mix easily with other gases. Okay, so if you have other, 2 or 3 different substances, gases are easily mixed. Okay, notably, particles of gases rarely come into contact with one another. All right, and sort of that's why sort of these properties of gases are the way that they are. We're going to talk more about the contact part of gases when we talk about kinetic molecular theory in the next topic. Okay, so the most important property of a gas is its pressure. Okay, well, maybe not the most important, but one of the most important properties is its pressure that it exerts on its surroundings. Okay, and to give you an idea of what pressure is, just think about what happens when you blow up a balloon, right? When you blow up a balloon, you are putting gas into the balloon, and the balloon expands, right, as you put more gas in. What you're doing is you're increasing the pressure of that gas. Okay, that's why it expands. Okay, the gaseous air particles inside the balloon are pushing against the elastic sides of the balloon, keeping it firmly propped up. That's what pressure is. Okay. Now, to demonstrate just how important pressure is, I've got this little video that we're going to watch here together. A lot of us take for granted how much pressure there is in our everyday world. Okay, and so I'll just let this video play, and we'll talk about it on the other side. Okay.
Bearded Science Guy here, and today I'm going to show you how to implode a can using atmospheric pressure. Start by filling a container halfway full of ice, and then add water until it's all the way full. Add about a tablespoon of the water to an aluminum can, and then place this can on a hot plate.
Okay, so what he's doing here first is taking this aluminum can, it's open, okay? He put a little bit of water in there, maybe he said what, about a tablespoon or a teaspoon, okay, so not very much water. He's going to heat it up until the water starts to boil, and so the can is currently it's full of air, okay, but what it's going to be full of soon is steam, okay, which is gaseous water, okay? So he's going to be taking the gaseous water, and you'll see what he does here in a sec.
Turn the hot plate on high and wait for steam to be pouring out the top. At this point, your can is ready to be imploded. Remove the can from the hot plate using tongs, and then in one motion, pour out the rest of the fluid and submerge the top of the can in the ice water. Bearded Science Guy here, and today...
Oops, I restarted the video somehow. Okay, let's go back here.
The can implodes because as the steam condenses back into water, there are no gas molecules on the inside of the can, pushing outward against the atmospheric pressure, allowing the atmospheric pressure to crush the can.
Okay, so what he said there was, your can was full of steam, okay? But when you bring the can into the ice bath, okay, and you seal off the entrance to the can, right? He's sort of dunking it into the water. The steam is going to relatively quickly recondense back into liquid water, right? It's being dunked in this ice bath. It's not on the hot plate anymore. So the steam that's inside of the can is, it's going to very quickly go from being a gas back into a liquid. Okay, so the amount of particles that are in the gaseous phase inside of the can are going to go from being, filling up the can to not filling up the can. There's not going to be enough particles in there to prop up the can. And so what ends up happening then is that the atmospheric pressure, which is just sort of the amount of air pressure that we have given the fact that we live on Earth, right, in a 20-mile deep ocean of air, okay? I know it's kind of weird to think of it that way, but, air on the surface of the Earth goes up, 20 miles or so. And so we live in this sort of ocean of air. And so there's immense amounts of air pressure sort of weighing down on us. We don't notice it because we're so used to it, okay? But when you put that can in there and seal off that entrance, the water particles condense back into liquid, and so there's no gas particles inside the can to exert pressure outwards on the walls of the can. And so what wins is the air pressure. The air pressure, which is very strong, as you'll see here, crushes that can. It's the air pressure that crushes that can in because there's no particles on the inside able to exert the force back out. Okay, so watch this again here.
Thanks for watching, Bearded.
Okay, so that violent motion there of the crushing of the can, that's all from the air pressure that's pushing down on us all the time. Okay.
Bearded.
Oops. Okay. All right. So hopefully that gives you a decent idea of what pressure is. It's just a property of gases that's always there, and we're going to be talking today about how pressure, volume, and temperature relate to one another. All right. So before we go any further, though, we do have to talk a little bit more about the units of pressure. Pressure is notorious for having a lot of, honestly, too many confusing sets of units that are used for its measurement. Here are a few this is not a comprehensive list, by the way, but here's a few units that you may see. The first one, and this is sort of originally how pressure was measured using a barometer. Okay, we're not going to get into all those details, but millimeters of mercury. Okay, that's one unit of pressure. I know this looks like a distance, right? Millimeter. And then what the heck is mercury talking about? Well, turns out that mercury is one of the few elements that is liquid at room temperature, okay? And it was used in early barometers. Okay, so a barometer is just something used to measure atmospheric pressure. And here I can show you. If we look up a barometer, a mercury barometer, let's just go. This picture looks good enough. Okay, so basically what you had here is a tube that's got some millimeter markings on it, and so atmospheric pressure would sort of push down on the mercury, pushing it up this tube. Okay, assuming that there's a vacuum here. All right, in the top part of this tube. And so you could measure the atmospheric pressure on any given day at any different location by using this device. Okay, this level would sort of raise or lower depending on the atmospheric pressure. If you took this same device and put it at sea level, okay, you're going to have a higher atmospheric pressure than if you took it on top of a mountain. Okay, and that's just because at sea level you're sort of deeper in that 20-mile ocean of air, and if you take it up on top of a mountain, you're not as deep. Okay, and so there's just less air that can push down on this pool of mercury, pushing it up the tube. So this level would come down as you go to the top of a mountain. This distance then from the base to where the mercury level goes is measured in millimeters, and so that's how millimeters of mercury is a unit of pressure. The more millimeters, the higher the pressure. The fewer, the lower the pressure. Okay? So, a little confusing. You don't need to know all those details. Just need to know that millimeters of mercury is a unit of pressure. You can also use inches of mercury, okay? You might see that sometimes. You can literally just convert between millimeters and inches, and you can get back and forth between those units. Anyways, moving on. Torr, T-O-R-R, this is named after like an Italian guy named Torricelli. 1 torr is the same thing as 1 millimeter of mercury. Okay, so these things are the same thing. All right, it's a 1-to-1 ratio. Okay, a more common, these are pretty commonly used. A more modern day unit is the standard atmosphere, ATM. Approximately 1 atmosphere is, sort of standard atmospheric pressure that we experience here on Earth. Obviously, it fluctuates from time to time and from place to place. But yeah, 1 atmosphere is typically like, about what we experience on an everyday basis. The SI unit, okay, so sort of like the official metric unit for pressure, is called the Pascal, okay, abbreviated capital P, lowercase a. A Pascal is a really, really small amount of pressure, though, okay? So oftentimes what you're going to see instead are kilopascals, thousands of pascals, okay? And like I said, this is often used instead because pascals are such a small amount of pressure. And then another one that's sort of more of like an American version of pressure is the pounds per square inch, or PSI, pounds per square inch. This is like what your tires are measured in, like if you use the little device thing to measure the air pressure in your tire. Hopefully you guys know what I'm talking about, the thing that has a little white stick that pops out. That's measured usually in PSI, or pounds per square inch. All of these things are units of pressure, and they can be exchanged using conversion factors, okay? And so really, the only 3 that you're going to see in AP chemistry problems are the first 3, okay? Millimeters of mercury, the first 4. Millimeters of mercury and torr, which are the same thing, okay? Standard atmospheres, ATMs, and then pascals, or kilopascals. Okay, those are really the only 3 that you're gonna, 3 or 4 that you're gonna have to work with in AP chemistry problems. So here are the conversion factors that you might need. 1 atmosphere is 760 millimeters of mercury, or 760 torr. Okay. Also, 1 atmosphere is 101,325 pascals, or 101.325 kilopascals. Okay, which means that 760 torr is the same as 101.325 kilopascals, right? Because those are both equal to 1 atmosphere. So you can use these conversion factors here to convert between pressures, between units of pressure, and that might be necessary depending on the types of problems that you're doing. And then obviously you can find other conversion factors for the other units as needed. Okay, you can find those online. Okay, one other thing about pressure. I mentioned on the first slide that different gases mix easily with each other, okay? And when they do so, you know, there's this concept that comes up called partial pressures, right? So let's say you have a mixture of three different gases, A, B, and C, okay? So it doesn't matter what these substances are, they're going to be well mixed. If you have, you know, A, B, and C, you can actually calculate what the partial pressure of any of these individual substances is based on its mole fraction. Okay, so let me actually write down some some terms here. Okay, so let's say that we have let's say 1 mole of substance A, 2 moles of substance B, and 1 mole of substance C. Okay, so we have 4 moles total. Let's also say that the total pressure, okay, so the total pressure, let's say this is, I don't know, 10 atmospheres, okay? We can use this information to calculate what is called the partial pressure of substance A. How much of the total pressure is coming from substance A versus substance B versus substance C. And it's this simple equation here, okay? Your partial pressure of A is going to be equal to your total pressure times the mole fraction of substance A. Okay, so that's what XA is here, the mole fraction. Okay, the mole fraction for substance A is just the number of moles of A, okay? So 1 mole of A divided by the total number of moles that you have. It's just that's what a mole fraction is. It's just the percentage in decimal form of your particular substance. Oops, sorry, not mole A, 4 moles total, right? So this is going to be 0.25, right? So the partial pressure of substance A would be equal to 10 atmospheres times 0.25, right? Or 2.5 atmospheres, okay? 1/4, right? So you can see here that the number of moles, or the mole fraction, I should say, of your substance is like directly related to the partial pressure, okay? Nothing complex here, right? So yeah, the total pressure of a substance is equal to the sum of its partial pressures, right, of the different components. And that is assuming, right, that your mole fractions are all adding up to 1, right, which they would need to, right? Okay, so that's not super complex, mostly common sense here. Let's move on. Okay, all right, so we're going to be getting into some gas laws. Gases, okay, so there's some things you have to understand about gases, all right? Gas particles are few and far between, like I mentioned before, and you know, they rarely, if ever, come into contact with one another. Okay, so due to the lack of interaction between their particles, gases, generally speaking, behave in a way that allows us to predict how their pressures, volumes, and temperatures are going to change under certain conditions using equations that are called gas laws. Okay, chemists and physicists have been studying these properties and how gases work for like 500 years, well, 400 years-ish, okay? So there are these gas laws that have been very well documented, experimentally determined to be true for ideal gases, okay? So before we get any further here, let's talk about what this means. Ideal gases. No real gas is truly ideal. A true ideal gas is a gas whose particles take up no space. So that's, first of all, that's why no real gas is ideal, okay? Particles do in fact have volume. The particles themselves, I mean, they do in fact take up some space. And also a true ideal gas has no interparticle interactions, meaning no intermolecular forces. And we know that that's not true either, right? Basically what we're trying to say here is that a true ideal gas would, contain particles that are, infinitely small points, not actual physical objects. So that's not quite true. We would also say that a true ideal gas, if particles, come into contact with each other, they're going to have zero interaction. They're going to maybe bounce off one another. They would bounce off one another, but they're not going to have any interaction. So no polar, dipole interactions, no dispersion force interactions, right? We know that that's not true either. So, that's how real gases deviate from being ideal. Okay, however, most gases are actually pretty close to being ideal. Most gases have very few intermolecular forces. They do usually have like some dispersion forces that can come into play, but it's not super significant. And also, a lot of gases, the particles end up being really quite small. Okay, so even though no real gas is ideal, for problem solving purposes, okay, you can treat gases as being ideal unless specifically stated otherwise. Okay, so these gas laws that these chemists and physicists have come up with, they are, they're only strictly true for ideal gases, but because most gases are close enough to being ideal, we tend to just use the gas laws and say, okay, there's going to be a little bit of error here, but not big enough for us to really have to worry about. Okay, and in cases where the error is large enough that you have to worry about it, there are some things that you can do. This is sort of outside the scope of AP Chemistry, but there are some things that you can do to sort of account for the error. Okay, so let's get into some of these laws. Okay, we'll go through them really quick. Boyle's law. Boyle's law tells us how pressure and volume relate to one another. Okay, it states that a gas's pressure and volume are. Let me fix that real quick. A gas's pressure and volume are inversely proportional, meaning if the volume of a gas increases, then its pressure must decrease, and vice versa. Okay, and like I said, this has been experimentally determined. So if you take a gas, let me draw on this graph here. I don't like these dotted lines that are here. They're not quite as clear as I would like. But okay, so let's say you have a volume, and let's say that our volume is exactly 20 something, okay, inches cubed, for example. Okay, and your pressure then would be, I don't know, what does that look like? Somewhere between 50 and 100, maybe, 70. Okay, inches of mercury. If you double the volume of your container, your pressure is going to have to be cut in half. Okay, so that's what Boyle's law says. It says that if you increase your volume of a chamber, right, and keep everything else constant, right, you increase the volume of your chamber, the pressure inside that chamber is going to go down. Okay, and it's like a mathematical relationship. Okay, they're inversely proportional. Okay, so let's actually look at this, right? If we have 20 inches cubed of volume and we expand that to 40, what we're saying is that the volume, if the volume goes up by a factor of 2, the pressure has to go down by a factor of 2. Okay, and you can see that here. This is sort of, if we have 0 and 50, this does appear to be about 35. Okay, so that's what Boyle's law states. Okay, and so you can use this, right? If the temperature is constant, if the amount of the gas is constant, you just sort of have this sealed off container. You can actually use Boyle's law to do some calculations. The pressure times the volume in some certain condition is going to be equal to the pressure times the volume in another certain condition. So if you know the initial conditions and you know the new pressure, then you can calculate what that new volume would have to be, right? It's sort of knowing 3 variables and having a missing one, you can calculate for the 4th one. Okay, we'll do some examples of this when we do the problem solving video. All right. Another law is called Charles's law. This one is a little bit more straightforward. Charles' law states that a gas's volume and temperature are directly proportional. Okay, so not inversely proportional, but directly proportional. What this means is that if you heat up a gas, okay, if the temperature increases, okay, then its volume is going to have to increase as well. And it's a directly proportional thing, meaning that if the temperature doubles, for example, then the volume is going to have to double. Okay. Now it does kind of depend on how you're measuring your temperature. Okay, we're going to be talking a little bit more about temperature, units of temperature in the problem solving video and in class, but that does generally hold true. Okay, and once again, there's another sort of form of Charles's law that we can use to solve problems. Okay, having 4 variables here. If you know 3 of these, you can solve for the 4th one. Okay? All right. And then we have Avogadro's law. Okay? Avogadro's law states that for any gas, equal moles or equal number of particles of a gas will take up equal volumes. Okay? What this means is that it doesn't matter what the gas is. Okay? You could be talking about nitrogen, hydrogen, argon, methane. Okay? It doesn't matter. If you have the same number of particles or the same amount of moles, right? Because the number of particles and moles are sort of fundamentally the same type of thing. If you have equal numbers of particles of any type of gas, those gases are going to have equal volumes. They're going to take up the same amount of space. Okay, and so you can see the sort of the representation here. If we have 6 moles, let's say each particle here is like 1 mole. If we have 6 moles in each balloon is going to take up the exact same amount of volume. Okay, assuming that the temperature and pressure are the same amongst all the balloons. Okay, so it doesn't matter what the gas is, it's just that number of particles is going to take up that amount of volume regardless of the gas or regardless of the substance. Okay, all right, and that brings us to the final slide here, the ideal gas law. You can combine all of these laws, all of these equations, into what is called the ideal gas law. And this actually ends up being the most used equation when it comes to gases. Just so you know exactly what these terms mean, P stands for pressure, V stands for volume, N stands for number of moles, okay, or just amount, okay, so moles. R is called the ideal gas constant. There are a couple different values for this, okay, but it is a constant, not something that's going to change. And then T is the temperature, okay? So the ideal gas law can be used to solve problems in a variety of different ways. So for example, if you know the state of a gas, okay, or if you know most of the things about the state of a gas, say you know how many moles you have, okay, you know what the temperature is, right? You can measure that with a thermometer, for example, and you know the volume of your container, right? You can look up the ideal gas constant, okay, so you know 4 of these things. You can use the ideal gas law to calculate what the pressure would be inside of that container, right? That's one way you could use the ideal gas law, all right? You can also use it similarly to how you would use like this equation, okay, where you have sort of 2 states, 2 different conditions. You can also use the ideal gas law to sort of predict, okay, if I'm taking my gas from one set of conditions to another, what would the new conditions be? You can kind of use it that way as well. The most important thing to pay attention to, though, when solving gas law problems are the units, okay? Because remember, we have like 6 different possible units for pressure, okay? Volume can be measured in a few different ways, right? That could be liters, or that could be centimeters cubed, or it could be inches cubed. You got to be careful there. N is usually going to be moles, okay? So you don't have to worry too much about that. T could be degrees F, right? Or it could be degrees Celsius, or really what it's going to be almost always are Kelvin. Okay, we'll talk about that more in the problem solving video, all right? And then R needs to be in the same units of these other things, okay? So if you have, say, pascals, right, for pressure, and let's say you have liters for volume, and you have Kelvin for temperature, you need to find a value of R that has units of Pascal, liters, and Kelvin, okay? Like those units need to be embedded in that value of R. You don't want to use the value of R that has atmospheres in it, for example, because then your units aren't going to work out and you're going to end up with the wrong answer. So we'll see some examples of this in the problem solving video. I'm going to do at least 2 different problems where we use 2 different versions of R. And FYI, if you're wondering, oh, do I need to memorize these units of R? The answer is no, okay? If you go into Canvas, and I think I actually gave everybody a hard copy of this at the beginning of the year. If you go into Canvas and look in your AP resources here, the reference sheet, okay, this is like your equation sheet that you're going to have access to on the periodic table. There are values of R here that you can use, okay? And so here's the gases, okay? You see these equations here, right? The ideal gas law, the partial pressures, right? And then here are the gas constants, okay? And you see how there are different, here, let me zoom this in a little bit. You see how there are different units present here, right? First of all, we got one that's like joules, what's going on there? Then you've got atmospheres, and then you have torr, right? And then, you know, you've got some of these conversion factors here as well. So you don't have to memorize these things necessarily, but you just need to be aware, you know, when to use the appropriate units. Okay? All right. Well, that does sort of cover it. Looks like I'm right at about 30 minutes, so it could have been worse. I think the problem-solving video is gonna help. A lot of this is kind of overwhelming when you first sort of hear everything, but then when you see what it is you're really expected to be able to do in terms of the calculations, it's not that bad. It's nothing worse than just some Algebra 1, Algebra 2 problems. Okay? All right, thanks for watching, and I'll see you guys in the next one.